Okay, welcome back. Today's lecture is on the topic of nitric oxide, and we're looking at a number of the roles that the nitric oxide has, and one of those is including an effect on the vasculature, and that kind of ties in with the cardiovascular stuff that we've done before. But we'll also look at it in its wider context. So, nitric oxide acts as a paracrine signal. That means it only affects the local area. Now, I'm just going to check here, I can see these slides. This can be edited out. Okay, we'll start this one again. Hello, welcome on to today's lecture, which is on the topic of nitric oxide. Nitric oxide acts as what we call a paracrine signal. That means it only affects a local area. So wherever you find it, that's where it's working. And the reason for that is, if you look, is because of its very short half-life. It's only got a half-life of a few seconds. So that means that very, very quickly, after it's released, it's going to be broken down and become inactive. Now, it's produced by the production of the enzyme nitric oxide synthase. So the name there determines exactly what it does. It's got the ASE at the end, meaning it's an enzyme. It's a synthase, meaning it's a synthetic enzyme. So this means that it's the synthetic enzyme that makes nitric oxide, or nitric oxide synthase. Quite often referred to as NOS, N-O-S. When it was originally discovered, back in the day, back when I did my pharmacology qualifications back in the early 1980s, was studying pharmacology between 1980 and 1984, and at that time we weren't aware that nitric oxide had the role it did. There was something that was found that was being released by the endothelial cells in the blood vessels that was known to relax those blood vessels, and that agent, as we knew it, was known as EDRF, endothelial derived relaxing factor. But here we are some 30 plus years, 35 more years later, and we now know that what we're dealing with in that compound is actually nitric oxide. Now, it's got a number of roles. It's bactericidal, it has that role. It can also kill various parasites, and it can also be effective against tumours. But one of the most important things that it does is it causes the vasodilatation of blood vessels, and that should be obvious from the fact that it's the endothelial cells of the blood vessels that release the nitric oxide, and it causes the nitric oxide, so the nitric oxide causes the blood vessels to dilate. In fact, nitric oxide is the most potent vasodilator known. So what happens is various neurotransmitters, for example acetylcholine, GABA, noradrenaline, they act on their receptors, and what they do is on the blood vessels they stimulate the endothelial cells to produce and release nitric oxide. And the nitric oxide then passes from the endothelial cells to the smooth muscle cells and causes the smooth muscle cells to relax. So basically, acetylcholine or GABA or noradrenaline, whatever the transmitter is, they are the first messenger in the endothelial cells. They produce the nitric oxide, and that acts on the smooth muscle cells, causing the production of cyclic GMP, which, as you'll remember from early on in the lecture path sort of sequence, is a second messenger. So here we've got the cells. So what we've got is we've got the generator cells. So these will be the endothelial cells, and the target cells will be the smooth muscle cells. So what you're seeing there, if you look at that diagram, what you see is that the nitric oxide synthase is the enzyme that converts L-arginine to nitric oxide. Well, actually, it's changing L-arginine to citrulline, and it's using oxygen to do that, but the byproduct of that reaction then is the nitric oxide, which is the target molecule we're after. The nitric oxide then goes to the target cell, which in this case, thinking of a blood vessel, that would be your smooth muscle cell. activates the guanylate cyclase, giving you the conversion of GTP to cyclic GMP, and therefore the resultant relaxation of the smooth muscle. Now we said that the enzyme that makes nitric oxide is known as nitric oxide synthase, and it exists in three forms: eNOS, iNOS and cNOS. And cNOS is sometimes known as nNOS. Now eNOS is called E because it's the endothelial nitric oxide synthase. And that's the one that's responsible for producing the nitric oxide in the endothelial cells that line the arterial wall, so the smooth muscle cells. So it gets produced in the endothelial cells and then diffuses to the smooth muscle cells. And once it's there, as we saw in the previous diagram, it produces the conversion or activates guanylate cyclase, which produces the conversion of GTP to cyclic GMP and gives you smooth muscle arterial dilatation. So therefore, that nitric oxide and this particular enzyme, they together play a critical role in the regulation of arterial tone and blood pressure as a result of that. So what we've got here is, we've got the agonist, okay? And the agonist then works on its receptor, activates the nitric oxide synthase, produces the nitric oxide, which goes across, which converts GTP to cyclic GMP in the smooth muscle cell, and the increase in levels of cyclic GMP subsequently reduce the levels of intracellular calcium, and if calcium levels fall in the smooth muscle, that means you're no longer getting the interaction of actin and myosin, and if actin and myosin don't come together, you don't get the sliding filament happening, therefore instead of the muscle contracting, the muscle relaxes, therefore you get arteriolar dilatation in the blood vessels. Now, various things can stimulate it. The acetylcholine, substance P, they'll produce nitric oxide, but also the shear stress. That's the actual pressure of the blood flowing through it. So that if the blood's pushing off these cells at a high pressure, that will activate nitric oxide synthase, produce nitric oxide, and relax the blood vessels to alleviate the pressure. So, if we've got the shear stress, what that produces is the entry of calcium. Calcium comes into the endothelial cells, activates the nitric oxide synthase, converts the arginine to the citrulline with the production of nitric oxide. The nitric oxide will then diffuse out of the endothelial cells to the neighbouring nearby cells, which in this case we're talking about the smooth muscle cells. Comes in, activates the guanylate cyclase, converts GTP to cyclic GMP, and then what we've got is we've got the conversion then of the ATP to ADP, and we get the result of smooth muscle relaxation. Now, let me just check that this diagram is quite visible, otherwise you might have to give it a right good look at on your screen, or you can just about see it on yours through the camera, so that's fine. What we're showing here is, now, this compound here is L-N-monomethyl arginine, which is an eNOS inhibitor. So what this is going to do is this is going to block the enzyme that makes nitric oxide in the endothelial cells. Therefore, if you use this enzyme inhibitor, nitric oxide levels fall, and if nitric oxide levels fall, then the smooth muscle will no longer relax, it will constrict. So what that should then do is that should elevate arterial blood pressure, because if the vessel constricts, pressure should rise. So does that happen? There's the pressure. We give the first dose of the drug, pressure rises, drops back down. Give the second dose of the drug, pressure rises. Give the third dose of the drug. So what you can see there is we have a dose-dependent response. The more we inhibit the eNOS enzyme, the more we see a reduction in nitric oxide. That results in a reduction in dilatation. The vessels then constrict, and we get elevations in blood pressure. And the blood pressure rises with each subsequent dose. So it's a dose-dependent manner. So what we've got on this slide here are the various receptors, and this is just various mechanisms that can result in either contraction or relaxation of smooth muscle. And we're obviously just dealing with this bit here, which is the L-arginine converted to nitric oxide by the action of nitric oxide synthase, coming down, activating guanylate cyclase, producing cyclic GMP, and therefore giving you the relaxation of the blood vessels. But that's just tying in with some other mechanisms that we'll come back and look at a later date. So, nitric oxide, exactly how do we get the relaxation? What's the actual detail of that mechanism? We've said that, okay, nitric oxide activates guanylate cyclase, that makes more cyclic GMP, but how does it actually happen? So if we take that mechanism on its own, the nitric oxide activates that enzyme, therefore the levels of cyclic GMP over here, they rise. So these are now